Hello student and welcome for DMS lecture. So in a previous lecture we discussed about the full design of diesel engine. So where we have seen that how we can design cylinder head, cylinder liner, then wet liner, then piston ring, connecting rod, and small eye bearings. So these are very important components or main components of the IC engine. So let's see one more problem about the design of petrol engine. Okay, so before starting of the design of petrol engine, um, I have prepared a standard procedure which I would like to share with you, where you can directly go to the design and based on the IC engine, which type of engine you are preferring. For example, it's maybe diesel engine or it's maybe and a petrol engine. Okay, so I'm just going to share the screen, the whole design. Okay, of it is visible properly. So this is a basic procedure for design of IC engine. So in this I have mentioned basic assumptions, whatever the basic formulas that properly it is shown over here. Then calculation of stroke and bore, it is nothing but design of cylinder. Then the design of cylinder head, cylinder weight liner. There are steps. These three steps also properly mentioned over here. Then design of stud based on two steps: gas force and preload force. Then empirical relation. So everything is properly arranged over here. Then design of piston में हमें पहले material choose करना है. Then crown thickness based on the maximum pressure and thermal condition. Then empirical relation. Then we need to calculate radial thickness of piston ring by using pressure criteria and empirical relation. Then calculating the number of piston rings. Then calculating the axial thickness of piston rings based on the thickness of piston ring and empirical relation. Then we are calculating the induced stress in the piston ring. Then the gap between the end of the rings. Then connecting rod design, why I section is important. Then based on the I section, we have first need to calculate the inertia forces based on the effective mass of piston, mass of connecting rod, and mass of unbalanced crankshaft. Then mass of piston we have calculated everywhere. Then calculating the normal acting force acting on connecting rod. Then we have seen the cross sectional area of connecting rod, that is I section. Then why I section is important. So this question may be asked in interview in oral. Explain why I section with IXX greater than equal to 4IYY is selected for connecting rod of an IC engine. So you must able to justify that by using this empirical explanation given over here. As the moment of inertia at x-axis, the area is equal to 11t square. So I-x-axis is equal to 419 divided by 12 t raised to 4. Similarly, for y-axis, the inertia is area is 3t cube uh, divided by 12, and the IYY is equal to 13112 divided by 12 t raised to 4. When we get a ratio of IXX by IYY, we get 3.2. So, but for connecting rod to be equally strong in both planes, so IXS is equal to 4IY, which means equivalent to 4IYY. So that is the a basic explanation you must have to written uh, in examination. Now next we to calculate the thickness of cross section in a proper manner based on the induced bending stress, total stress, then design of small eye bearing and big eye bearing. One more thing which is we have yet haven't discussed, that is a design of crankshaft. So design of crankshaft, that is a calculating the crank pin diameter based on the bending strength and the shear strength induced in the crank pin. Then calculating or checking the crankpin details for bearing pressure, then design of main pin bearings based on uh, the diameter. We have calculated the diameter based on the bearing stress, then calculating the dimension of crankshaft waves. So it is subjected to bending stress, and based on that we have calculated. Then secondly, it is considered as a direct stress, and based on the result stress we are calculating or checking whether it is safe or not. Okay, so this design I have given the link of this design in a description box, so you can go and download from SlideShare, where I have stored over there. Okay, so let's see the example of the petrol engine. Okay, this is a December 17 questions asking for 15 marks. The procedure in IC engine, you may be design of diesel or petrol. Most of the standard procedure will be same for both. So that's why I have prepared a standard procedure for design of IC engine. Okay, so let's start with the problem. Design following the component of the single cylinder 4-stroke water cooled petrol engine to develop a 40 kilowatt at speed of 2500 rpm by making a suitable assumption and within its gauge. Assume a compression ratio as 7.5. What we need to determine? Cylinder, liner, cylinder, that is cylinder head actually, and stud. So these parts we need to be designed. Okay, let's write down what are the standard things or given input data. So type of engine, it's a 4-stroke petrol engine. It's water cooled. Brake power it is given is 40 kilowatt. Speed n is 2500 rpm. Compression ratio RC it is 7.5. With a similar procedure of design of diesel engine, first we need to calculate the bore diameter and the stroke length. So based on this, we are able to design cylinder. So basic assumption, as the compression ratio is 7.5, and for 4-stroke engine, the mechanical efficiency is 85%. Referring page number, referring design data book of Kale Khandagle, page number 6, table number 3.5. Mean indicated pressure, that is P mean 1 megapascal, that is 1 into 10 raised to 6 Newton per meter square. Referring Kale Khandagle, page number 5, table number 3.2. L by D ratio, L by D ratio, we are assuming equal to 1. Page number 6, table number 3.6, 3.7. Then maximum pressure from Kale Khandagle, page number 7, table number 3.9. The P max or maximum pressure is equal to P1 into RC raised to gamma. So calculating maximum pressure, P max is equal to P1, that is a indicated pressure, P1 that is 1 megapascal multiplied by RC raised to gamma. gamma is equal to 1.4, RC is equal to 7.5, so it's equal to 16.79, approximately 17 bar. Now calculating the bore and stroke dimensions, as the mechanical efficiency is equal to brake power divided by indicated power. So mechanical efficiency is 85%, brake power is 40 kilowatt. So we can able to find out the indicated power, that is 47.06 kilowatt. So indicated power is equal to uh, indicated pressure multiplied by length area into n, where n is the number of strokes. How we can calculate? The number of strokes is equal to n divided by 2. So n is 2500 divided by 2. As it is 4-stroke engine, that's why it's divided divisible by 2, as I previously explained, because it required two movement of two 360 or full revolutions of the crank. So small n is equal to 1250. Putting all the dimension, L is equal to D, as we know L by D ratio is equal to 1. So putting all the values in equation in the form of D. So based on the indicated value, or IP 47.06 into 10 raised to 3, we are able to find out the diameter of the cylinder. So D is equal to 0.142, that is 142 mm. We can modify it to 145, which is nearest standard value of the diameter is available. So as we know that L by D ratio is equal to 1, so diameter is equal to length is equal to, or you can say stroke is equal to 145 mm. You can refer Kale Khandagiri, page number 6, table number 3.6. So now we have just designed the cylinder, that is the main dimensions are bores and stroke. We have calculated now. Now next one, we need to design a cylinder head with the weight liner. So cylinder liner we can design based on the minimum thickness. So we can first of all calculate what is the minimum thickness is required for cylinder liner. So T1 minimum is equal to D by 2 as D plus 0.4 P max divided by ST minus 1.3 P max raised to 1 half minus 1. Refer Kale Khandagiri, page number 12, table number 4.5. For this cylinder, or we can say weight liner, the material should be selected previously. So that material is a stainless steel having a design stress of 90 megapascal, and the maximum pressure is 17 bar, which we have already calculated. So it is a 1.7 megapascal. Now putting all the values of D, SD, P max into the equation, what we get. So minimum thickness required is 1.18 mm. Okay, so by using the equation minimum thickness criteria, we get thickness is equal to 1.18 mm. Now we need to calculate empirical thickness based on the empirical relation. So D1 is equal to Di divided by 15. So internal diameter Di is equal to 145 divided by 15. So T1 is equal to 9.67. We can modify or round up to 10 mm. So from equation 1 and 2, whichever the higher value that we can consider for design. So here the value of thickness, or the thickness of the liner T1 is equal to 10 mm. Now calculating the pressure induced. So Sx is equal to P max into D divided by 2 T1. So putting all the values, and we can calculate the pressure induced. Sx is equal to 12.325 Newton per mm square. Now thermal stresses induced inside the cylinder. So St is equal to E alpha delta T divided by 2 into 1 minus mu. Referring Kalekhand page number 12, table number 4.5. So material is we have already selected that steel C35. Kalekhand page number 1, table number 1.1. Value of Young's modulus E is equal to 20.6 into 10 raised to 4 megapascal. Mu is equal to 0.3, alpha is equal to 11.1 into 10 raised to 6 per degree centigrade. A delta T temperature difference over the walls is 100 degrees centigrade. So putting all the values, what we get, the thermal stresses induced are 163.3 Newton per mm square. Now total stresses we need to be found out. So total stress should be less than 200, other then and then only our design is safe. So that condition we could check over here. So St is equal to Sx plus S small t. So addition is 175.6 Newton per mm square, and allowable stress is 200 megapascal. So hence our design is safe. Now the design of stud, third one. Calculating the design of the stud is based on the maximum gas force. So Fg is equal to P max into pi by 4 t square. P max is 17 bar, diameter is 145. Here we are converting diameter into the meter in the form of in the unit of meter. So Fg is equal to 28.06 into 10 raised to 3 Newton. So F max is equal to Fg divided by Ng, where Ng is the number of studs. We are using 4 number of studs. So maximum gas force applied on each stud, that is F max is equal to 7014.5 Newton. So calculating again the pre-loading forces in the stud, that is FPL. So FPL is equal to M into 1 minus L into F max. So M is a stud tightening coefficient, which is 1.7, 1.75 without gasket. If a gasket is there, then the value gets changed. FPL is equal to 1.75 into bracket 1 minus 0.2, 28.06 into 10 raised to 3. So the preload force is 39.28 into 10 raised to 3 Newton. Now calculating the total load on the stud, individual stud, that Ft is equal to X into F max plus F into PL. So value of X is equal to 0.2. So after the calculation, what we get, Ft, the total force acting on each stud is 44.9 into 10 raised to 3 Newton. Now calculating the dimensions of the stud, material we have selected SAE 2330. Then design stress of that material available SD is equal to 145 megapascal. So SD is equal to FT divided by AC. That is the area, core area of stud. So 145 is equal to 44.9 into 10 raised to 3 divided by AC. AC is equal to 309. Calculated or induced area is 103.65 Newton, mm square. That area we have calculated. Now we need to choose a standard area which is nearest one or greater than but nearest one. So referring Kalekhand page number 17, table number 4.9, the nearest area is 311 mm square of M22 bolt with the pitch of 1.5 mm. So it's very simple to design, as you can just follow the procedure, which is standard procedure. I have shared the link of that this standard procedure. This is a standard procedure. I have shared the link in a description box, so you are able to design any type of IC engine. It may be petrol or it may be diesel. The design procedure will be same, so few parameters will be changed. That parameters you can easily find out over here. Okay, so I hope you will understood the design of IC engine. I request all of you, you can start your complete your all assignments and submit as soon as submit before the last date. Okay, so thank you very much for joining the DMS lecture.